Hello.
Hey, hi Philip. Kunal this side. Uh, just a minute. Actually,
Hi.
we are in some other meeting, so just give me like a minute.
No problem. No worries.
Hey Philip, hi. You can try presenting your slides now, so that we can check it.
Yep.
Yeah, the slides are visible.
Very nice. I will see. Also, this is
Yeah,
visible.
they're changing.
Good.
Yeah, we
So
can
I think
start at
that's it.
yeah, we can start at 3:35. Like
At what?
uh, like at UTC 10 fair.
Yeah. Okay, great.
Hello. Yeah, Dr. Philip.
Yes.
How are you?
Hello.
Hi, how are you?
I'm good, thank you. How
Yeah,
are you?
I'm good. I'm good. Thanks for accepting our invitation.
Yeah, I'm glad to be here. Thank you for the invitation.
So we'll wait. We do have some TC220 members, including Andrew. So he may join. Then IGS, Indian Geotechnical Society members also. So we'll wait for some more time because it's still, we have, I think, 7 more minutes.
Yeah, exactly. I also already tried to share my screen so everything works. So if you start, I'm ready.
Thank you so much. So what time is there at your place?
11 in the morning.
Oh, great, great, great.
Yeah, so my day is still ahead and yours is slowly coming to an end, right?
Nice, nice, nice. Actually, this lecture series we are starting as a cut and riser event every month as we are doing the international so the conference symposium on field monitoring in 2026. That will be
Oh,
at
okay.
okay. I'll be the convener for the conference. So as a part of that conference, we are trying to do this as a cut and riser events. So every month we have a lecture from different, experts across the world on field monitoring. So this is the 5th lecture.
Oh, great. Yeah, that's very nice initiative. Yeah, sounds very good. Especially to have it like internationally, then
Yeah,
you
yeah,
get a really good
and we are
overview.
recording it, and we are recording this, and it will be on ISMG TC220 YouTube channel and also Indian Geotechnical Society YouTube channel. So once the link is there, I'll share it with you, or my student Kunal will share it with you, so you can share it with other people.
Okay, that's great. Thank you.
नहीं मैं हेल्प नहीं जाऊँ
जब मैं बोल रही थी तो
नहीं मेरा
Good afternoon, Dr. AP. You are in mute.
Very good afternoon.
Yeah. Dr. Philip, Dr. AP Singh is our Honorary Secretary of Indian Geotechnical Society now.
I'm very pleased to meet you. Hi
Yeah,
from
good
Austria.
afternoon, Dr. Philip. Nice to see you and listen your lecture.
Thank you. I'm happy to be here.
Yeah.
And Philip, you should plan to visit us also for 2026 conference.
Yeah.
Yeah, I've never been down there, so yeah, would be great. I would be happy to come.
So,
Yeah. What is the time in Austria? Is it morning or working time?
Yes, now it's 11.
It's 11. Okay, great.
Yeah. And at your place, what time is it now?
It is 3:30.
3:30. Okay.
3:30 p.m. I think 4.5 hours thus ahead.
Mm-hmm. Yeah, I
Yeah.
also had to check with my calendar when
Yeah,
when the
yeah.
time is, and but it's good. I'm here. It seems at the correct time.
Yeah.
hello Dr. APC
Andrew. Yeah, Dr. Andrew, good afternoon.
Dr. Andrew, nice to see you. How are you?
Hello.
Happy New Year.
Yeah.
You are in mute.
Sorry, I didn't see that. Yeah, I'm very well, thank you. How are you?
I'm good. I'm good. So Happy New Year.
Yes, it seems a long time ago now.
Yeah. We missed you in the last lecture series.
Yeah, I'm sorry. It's a very busy period for me at the moment.
Philip, Dr. Andrew is chairman for TC220 of ISMG on field monitoring in geomechanics. And he's a big supporter for this lecture series and for the 2026 conference at IIT Indore.
Great, nice to meet you.
I'm looking forward to your lecture. Nilima, I have a few slides to show at the end.
Exactly,
Just
I know. I'll start that.
usual.
That's why I'm starting now. Let people join. And anyway, we are recording it. And I think, our recordings have been widely seen. So I can see that from the numbers also, views. And that's a good thing. So let's start. Good evening and good morning, everyone. To all the participants, myself, Nilima Satyam, professor at IIT Indore. And I'm happy to host this event, today's talk by Dr. Philip. First of all, I should thank Dr. Philip for accepting this invitation to be our speaker today. Thank you, Dr. Philip. And I'd like to request Dr. Andrew, who is a chairman for TC220 and who is instrumental and big supporter for the entire event and, to my conference in 2026. So, Dr. Andrew, please.
Oh, thank you. I welcome everybody. It's nice to see so many people attending these lectures. It's become a very popular part of the TC220 program, and it's very pleasing to see how well it's going. Do you want me to come back at the end and give my notices, Nilima? Is that the easiest thing to do? Sorry, you're on mute.
So I think you can introduce about TC220 and other things, then we will start the lecture. I think that.
Okay. I'll give I'll share my screen now. Just give me a second then. Okay. Can everybody see that?
No.
Not yet. Now, hopefully. You can see it now?
Not visual.
Still not seeing it?
Yes, it is.
Oh, okay, excellent. Okay, so notices. Events that are coming up, TC220 events. In a couple of weeks' time, the British Geotechnical Association will host a meeting on the observational method. This is a half-day meeting supported also by TC206. It's an in-person meeting, I'm afraid, so there won't be an online aspect to it, but we will hope to record it and put it somewhere afterwards. So look out for the recording. The next event after that will be the 10th International Course on Geotechnical and Structural Monitoring. This is something that was started many years ago by John Dunnicliffe and was hosted in America for many years. It was brought to Europe by Paolo Mazzanti from the University in Rome and NASCA. And it's now going back to America for the 10th anniversary issue. It's going to go back to America. I'm not sure if it will stay in America or whether it will just be for the anniversary, but it's going to be held in June and will be in Denver in Colorado. Shortly after that, or roughly about the same time, in fact, is the International Conference on Site Characterization, which is going to be held in Barcelona this year. And there's going to be a mini symposium on field monitoring. This has been organized by Josep Raventos from Socotec, and the support for that has been quite wide. I think he's got quite a good program of events. I'm not sure exactly who the speakers will be yet, though. In August, we have a workshop at the European Conference on Soil Mechanics and Geotechnical Engineering, which will be held in Lisbon, in Portugal. And on one day, we have allocated to a workshop on the subject of the importance of field monitoring in geotechnical engineering. The priority on how can we specify quality in geotechnical monitoring and that will highlight the work that's been done by the ISO working group on producing international standards for INEM. There'll be a session with TC206 on the role of field monitoring in the observational method, and that will be pulling in participants from both of the technical committees. After lunch, we'll have a reprise of the Dunicliffe Honour Lecture that was given by Alan Marr in the last international symposium in London, and we'll finish the day with a workshop session on how can we incorporate field monitoring into our educational programs, so university programs in particular. I'll mention the 12th International Symposium on Field Monitoring in Geomechanics that will be held in India. I'm sure that Nilima will talk about that in the coming through. IW all the 660 followers as of this morning, so we're growing fast there, and this is where you'll find out most of the news about what's happening in TC220. So all of these international lectures are publicized through the LinkedIn page. There are podcasts around now that are related to monitoring. In particular, there's one that's been run by Andre Silva in Brazil, which is aimed at people who speak Portuguese. You can get a translation on the YouTube website, but he's focusing very much on the Portuguese and Hispanic people. And finally, I think all of these lectures that has been organized very well by Nilima are on our YouTube site, which you can find by just searching for ISSMG TC220. And that's all of my notices. So thank you very much for the time, Nilima, and I look forward to listening to Philippe's lecture.
Yeah, thank you so much. And before starting, we have our Indian Geotechnical Society Honorary Secretary, Dr. A.P. Singh, to just say a few words so that we will start the lecture.
Yeah, actually, this is I think fifth or sixth lecture of this series,
Fifth one.
it is a fifth one. This is the fifth one, so it's a very on the fast track we are going. And for regarding ISFMG, we are very soon we are going to start podcast also with the help of Nilima and all regarding that conference. And regarding this Indian Geotechnical Society annual function mega event is organized every year, and this year it is IGC Indian Geotechnical Conference will be organized at Aurangabad in the last month of the year 2024. So you all are invited and can join the conference. So that's all from my side.
So thank you so much, Dr. AP. And without making any delay, so I would try to take this to introduce our today's speaker. And I feel like it's my honor to introduce you to all the participants here, Dr. Philip. So Dr. Philip is a geographer and a geomorphologist, and currently working as a senior scientist at the working group of geomorphological systems and risk research at University of Vienna in Austria. He is interested in landslides and risk research, and he's co-leading a core facility of eSurf Lab at the University of Vienna in order to improve the knowledge for processing the concerning slow-moving landslides, which are very, very, the creep behavior of the geotechnical part. And his interest is also very much on glacial geomorphology And because of climate change, we do have so much of issues even in the Himalayas, Indian Himalayas. So I think it will be great to listen to you. And he obtained his PhD from the University of Bonn in Germany on the paleoclimatic significance of the pre-glacial landforms in southern Norway. So with this very brief introduction, I request you, Dr. Philip, to just start your lecture.
Yeah, thanks very much, Nima, for the very nice introduction. I feel very honored and happy to be part of this lecture. And yeah, I think to avoid further delay, I will directly share my screen. I hope you can see it.
Yes.
Yes.
Yes. Okay, great. So yeah, as I said, I'm very happy to be here and be part of this lecture series. And today's talk will be about, or is titled Long-Term Monitoring on Slow-Moving Landslides in Lower Austria. And yeah, as was already said, I'm the senior scientist at the University of Vienna in the Department for Geography and Regional Research. And I'm part of the Geomorphological Systems and Risk Research working group. And the leader of the working group is Professor Thomas Glade. I'm sure some of you are aware of him. And on the picture here, you can see the other persons of our team, which is in me and our technician Robert Kanter, and our two PhD students, Eduardo and Alejandra, and our student assistant Benny, which are all of which also participate, of course, in the research and also helped preparing some figures and some assisted with some slides. Thank you already in advance for the group. Okay, what can you expect in the next, let's say, 40 minutes? So I will first briefly go through our working group that you're aware of, which perspective we are talking about, and then generally about the landslide issues we have in Lower Austria. Then I will talk about the methods we're applying in at our study sites. Then we will have a deeper look in our study sites, and I will finish up with some results from our numerical modeling, and then sum up, and yeah, we'll see where we go from there. Okay, so as already mentioned, I'm part of the University of Vienna, Geomorphological Systems and Risk Research, our working group. What are we focusing on? It's about, for once, climate change-induced environmental changes in high mountain areas is what we look at, but also the effects of environmental change on our society. So we are not only focusing on, let's say, the natural sciences, but also a bit on social sciences. So as a geographer, and maybe some of you also have a background in geography, can relate to that, I hope. And what is important for us is also not only looking at the hazards, but also at the risk component, looking at reduction of risk associated with landslides in our study areas and beyond, of course. And other members of our working group are working also on fluvial systems, fluvial geomorphology. And yeah, if you want to know more, you can have a look at our website, geomorph.univ.at. And yeah, so now, as you saw, we have, I think, around 25 people in our working group. We have a lot of different projects, but one which we'll focus on also today is the so-called NÖ-Slide project. NÖ is the abbreviation for Lower Austria in German, and slide, I think you know what that is. And basically the project is about the long-term monitoring of slow-moving landslides in Lower Austria. Let's say the relevance and the background is that landslides are the most common natural hazard in Lower Austria, and is often induced by heavy rainfall events. And the reason why Lower Austria is so, heavily affected by it is due to the lithology. We have deep weathered, heavy clay soils. We will come back to that in a minute. And yeah, the hazards have some impacts with damage to infrastructure, for example, when one of the two of the research sites, they are located next to a very important road in a valley, which yeah, would cause high impacts also in socioeconomic sectors. That's why we're looking at. And what are we focusing on? So we started the monitoring system already more than 10 years ago. This was already before before I started in Vienna. I started around 3 years ago. So it's running since already a very long time. And we also, we implement well-known and well-used methods, but also want to have or want to test newly or not even up to now used methods and innovative methods, see how they can apply it in landslide research. And of course, we're also having a look at the risk analysis and evaluate them. And also one of our focus is to raise public awareness. This is why we have a very nice website, which is also displayed here. So Nöslide AT, where also the people who live in the surroundings, they can have a look at data, and the data are displayed real time on this website. So all the different study sites are equipped with different systems, which we come to in a minute, and some of them here in real time. And I know from the landowners there that they're very happy about it, and they check it regularly, that they know what is going on their property. Okay, so I think first we start with a rather brief overview about landslides in Lower Austria. So here you have a map of Lower Austria, and in the mid section here you can see Vienna, where I am sitting right now. And basically here you see it's a landslide susceptibility map. In yellow and the medium in yellow. They are the landslides which were mapped by us in 2014, and you can see that in this time nearly 13,000 landslides were documented in Lower Austria. And we had a follow-up project which just finished last month, where we re-evaluated our susceptibility maps with the landslides which happened since 2014, since this publication. And the landslides which happened in the last 10 years, they were nearly all of them in the susceptibility areas mapped or created by us, which were in the high area. So this approach worked very well. And yeah, this is where this is why we're doing our research in Lower Austria. And the reason why this high susceptibility is located here in this, let's say, in this string west of Vienna. You can see here in the lithological map, this is called the Flüsch zone, which is, Flüsch is a Swiss word which indicates flowing. So you see that also people in the past, they already somehow got a notion of that the landscape is quite dynamic, and they called it like this. Our studies are located in the Flüsch zone, or in this darker green area, the so-called Tippen zone, which has a lot of marl and limestone. And just south of it, we have the northern Ceres Alps with a lot of limestone, dolomite, and so on. And this is where our study sites are located, here at the Flüsch zone. Here our 3 study sites, the Hofermühle here, the western part, and then we have the Zalcher landslide and the Brandstadt landslide. Just before we go into the methods, I wanted to also stress that, like it was in the title, that we are studying slow-moving landslides. So we are not looking at catastrophic failures. As for us, it is important. The big advantage of the slow-moving landslides is that we can really have a look at the processes and the long-term dynamics of the material, how it reacts to different times of freezing, of thawing, of rainfall, of snowfall, anthropogenic influence. And this is why we are now looking at landslides which are moving centimeters, decimeters per year, but not catastrophic failures. And then also, of course, you can study, you can learn a lot from them, you can study a lot, but our focus some slow moving landslides to understand the processes in a good way. Okay, so now we'll jump into the methods. What are we doing? What are we implementing in study areas? So maybe before we have like a basis of monitoring devices in all of the 3 study areas, but some of them we have some, I don't know, special things we're looking at. Some we cannot apply some of the methods. So yeah, you will see it's a bit of a mixture, but we have like a common ground also for all. And one common ground for all of them is, of course, our meteorological station. All of them are equipped with a Campbell meteorological station. The data is recorded every 5 minutes, and we have also a Wi-Fi internet connection there. So it is always being transferred directly to our University of Vienna, and as you saw, it's also publicly visible. And what kind of parameters are we looking at? So it's what you would expect. We have air temperature, air humidity, solar radiation, wind speed, and precipitation. And I don't know if you can see my mouse, but here on the right-hand side on the picture, you can see also a distrometer we are having. So we can also say something about the droplet size and distribution of the rain drops during a precipitation event. And this picture is also quite nice because it exemplifies a little bit the scenery of our study site. So you can see it's more or less steep. It always depends, of course, what you're looking at. If you're high mountain areas, it's a bit different. So we are here, we would call it a rolling hill country in Lower Austria. And you can see that it's when it gets steeper, it's covered in, we have forest cover, but if we go a bit to the lower slopes, it's anthropogenically influenced. We have food production for cattle, for example, and this is then also used by humans, and also we have anthropogenic influences by drainage pipes, which I come to later as well. But this is basically, if you want, how our study look like. Okay, another method we're using are, of course, UAVs. We are using it for recording of high-resolution aerial RGB images. As you know, it's quite easy to use. Also, in our case, in Austria, need a special license to do it, and yeah, we always have to take care to be on the legal side. And so, yeah, that. And in the end, we are doing some structure for motion. With reconstructing of 3D coordinates from 2D images taken from different perspectives. And with this, we create a point cloud. And yeah, we're trying to doing this as a time series. So regularly we go out in the field. So usually we try to go out or at least we go out every month, sometimes more often. And so it's also weather dependent, with the surveys or not. But yeah, we're trying to do it at least once a month or every 2 months. And maybe to get an idea from here in Vienna to our study sites, it always takes 1.5 hours by car. Our field work. Yeah, and how does it look like? So just a small idea on Brandstadt, the landslide, which is our newest one, which is very newly equipped just since last year. And you can see here the auto photo on the left-hand side with cars in the lower part of the picture. And yeah, you can see already, maybe also from the auto photo, if you have some experience, you can see some low base structures. But if you look at the EM from the UAV, you can see on the left side of the street some base structures, and you can also see some anthropogenic structures on the right-hand side, and also slope structures basically everywhere, which is a good indication for us that something is happening, that we have some some surface displacement. Yeah, then what I already said, we can create also some DODs, DEMs of difference. From this, on the left-hand side, you can see the elevation change in meters. Red is like the source area where we have negative elevation changes, and the blue or greenish areas show us some elevation gain. And yeah, if you see here from the arrow on the left-hand side picture, you can see the A's with the red circles. These are our inclinometers, which I will come back in a minute. And you can see that we have surface has some cracks, and on the lower right picture, you can see also the base structures. So the structures we see in real life, let's say, we can also detect very easily. Then what we're also doing is terrestrial laser scanning. In the last years, we always use the Riegel VStat 6000 for regular surveys. So we tried always to have several multiple scan positions around the slope, so around the valley. So we just looked for some places on the other side of the valley to scan it. When maybe some of you also apply this, you know about the challenges of this method. We often have line of sight problem, particularly in this rather woody area. So you can see on the lower part of the picture here the shade effect, which is particularly in this area not so nice for us, because also here we have some movement, or also in the upper area here a lot of movement, but we cannot detect it really good. The laser scanner with this laser scanner from this perspective. So this also is far, or the scan distance also leads sometimes to a rather coarse solution of resulting point clouds. So we decided to invest some money for a new laser scanner. So since last year we have the Riegel VSat 2000i, which also allows us new approaches, which is, for example, we can, for example, walk around and do faster and easier scans with a better resolution, with better point clouds. With this, the line of sight problem is greatly reduced. For example, with this scanner, you don't need to, it references itself, and it can have some, how to call, I forgot how they call it, but you can basically register it at one time and then make a walk also through forest area, for example, and it knows every time where it is. So it helps us a lot. But as I mentioned, it's more work and time intensive, and we have a great data volume. And we started last summer. We had some field campaigns already. But yeah, we are further learning and also working on it. We're also working together with the Riegel company, and yeah, it's always a great help. And yeah, we are can make very good progress in this, and we're happy that we can use this laser scanner. Additionally, I already mentioned the inclinometers. I think most of you know how this method works. Our colleague Edo here provided some insights how it basically looks like. So the inclinometer provides us information on the subsurface movement. We always install it with this machine. So we have on the left-hand side screen machine. You see it's our drilling rig, and we can go up to, I don't know, I think maximum was maybe 13 to 14 meters deep, and we extract every meter also a core with sediment. So we have a look at this in our lab. When we extracted the sediment cores, we integrate these long tubes, and which are indicated here in this graph in red. And then we go there, as I said, every month to measure with a probe the displacement, the subsurface displacement. And we do this every 50 centimeters. And this allows us to identify potential shear surface. You can imagine that also this method has a limitation, because if the movement is too too much, then the tube is inclined in a way that we cannot enter the probe anymore. So then for us, we always call it it's sheared off, and then we need to install a new inclinometer. So on the one side, it's good because we see that our slow-moving landslides are moving, but of course, it's always extra work also to install it again. But we have a good team, and which is highly motivated also to go out and here at this time of year when it's winter around, I don't know, 0 degrees, we also go to the field and do this kind of work. Yeah, and with this deformation, we can create some nice graphs, which I will come to later. Yeah, and here, as you saw already the drilling rig, and on the right-hand side, this is how our monthly measurements look like. Go out in the field, yeah, try to measure as often as possible. Here, then you see, as promised already, some results, how the inclinometers results look like. So here is again the Brandstadt slide with the subsystem 1, which is marked here in the left side in yellow, and the A is indicating the location of inclinometer A. And here you can see the graph with the depth of around 6 meters. On the y-axis and x-axis shows us the cumulative displacement, which starts at around or goes down to around 4 meters. And you see that it's cumulative, let's say, until January 23rd. I think the last field day was on Tuesday. So the results here are very fresh. So you already have a of around 11 to 12 centimeters downslope. And yeah, this is why also we expect this inclinometer to share off probably latest in 2 months, because we now have we had now a rainy period, and also today is a snowy period, and after we still expect 1-2 months of snow, and when after snow melt, we also usually see the most movement or displacement, and then we expect the inclinometer A to shear off very soon. What we also do is dynamic probing heavy, DPH. So you have to turn your head a little bit to see it properly, but we thought this is a good way to display it, that we have a metal rod which is driven into the soil by 50 kilos, and the number of blows required to put it down, the rod in the soil, is documented for a certain depth interval. We usually use 10 centimeters, and the number of blows we need to put the rod in 10 centimeters provides us an information of resistance. And if the material changes, we also expect a difference in resistance. And with this, we also try to see or to identify shear planes, which is working quite well, and which we can also somehow put together with the information we have from the inclinometer. So that gives us quite a good insight of the subsurface structures we're having. In Brandstadt, we are also since last year using, because this inclinometer and the DPH gives us point information, but we also want to have, of course, aerial information, how structures also change in an area. So we also implement ERT measurements, and also induce as IP measurements, induce polarization with the geophysics from the Technical University of Vienna. So this is how we want to get information at the broader scale. So if we look at the results from dynamic probing heavy, the profiles you can see on the map, and yeah, you can see here the different DPH points we're having and the depth. So we go up to nearly 11 meters, and you can see here the different resistances. Also, the legend here shows you let's say the thresholds. So we say below 3 blows, and then below 8, below 15, then everything which is above 45. Also, then we stop, because material is not really designed in a way that it can take too much of those blows. But you can see here this nice graph, which shows us the difference of resistivity. And if we look here at the DPH point B, you can also see that in around 4 meters, something changes, which also aligns in a way, results from inclinometer, even though it is a bit further down slope. If we look here at the profiles, you can see this is now again where deep inclinometer A was, and you can see that it's like a cross profile of the surface in black. Red, you can see the potential sliding plane, which we drew the line basically where we had the most change in the DPH resistance. And yeah, with this idea, it's like the first indication of how we could get to a potential sliding plane, and this depth, of course, we need also for our modeling approach. Of course, as I said, for us, we also, it's often like that, but for us, we also have quite a focus on the hydrology of the slope. So as mentioned, we record the precipitation with the meteorological station every 5 minutes. The same is true for piezometers we have. So it's a bit dependent on the slope on the research side, study side. We have 2.8 side, and we also have TER probes, at least 3 locations at each site, where we also have at 0.5 meter intervals up to 2 meters, which is the maximum depth we have, which also has a recording of 5 minutes of the soil moisture. So you see we have really a lot of data coming in every day or every 5 minutes from the systems, and you can imagine that it's also quite some work to keep all the systems going and to check that everything is working at all 3 sites. So this is happening at all. And yeah, here on the map, you can see some kind of a small summary of what we have in Brandstadt. This is, as I said, the newest site. So we have a lot of DPH points. We have the inclinometers in red. We have the piezometers in blue. And then additionally, you saw the TLS and the UAV we have. So you see, we put a lot of effort in. And if we have a look at a quick glimpse into the results, how the hydrology looks like here, we have the top figure, cumulative rainfall, and also the hourly precipitation. And we can see that our system or what we record works quite well, because in the beginning we had some problems, and also how this precipitation is in line with the response of the piezometers. The one piezometer is in deeper, or we could get deeper. That's why we usually get a signal after rainfall, and if not, it's the groundwater table is not hitting exactly the end of our piezometer, and with the other one inside the groundwater table, but also reacts the precipitation, which is quite good. Okay, so I'm now finished with the methodological part, and now we will, I'm not finished with the methodological part, but this was now the first part, the focus on the methods itself. Now I will get more into the sites and what kind of methods we're using there, and show you some results of the different sites. So to start with that, here you have an overview of the different sites. So the site we now talked about most is Brandstadt, and we will come back to that in the very end again. And first, I would like to talk about Salcher and Hofer Mühle, which are the oldest sites we have. And from also my introduction, you could imagine that all sites are not so far from each other, and that they therefore could be quite similar, but they have quite distinct differences, why we think it's worthwhile to have a look at them also separately. So first, the Salcher, it's the recently active area is relatively small, only with 4,000 square meters, but the potential activatable area is much more bigger. And here we have a displacement of around 10 centimeters per year. So this is also our, let's say, most quiet side, even though the last year was most active since the last 10 years. So this also showed us the importance of a long-term monitoring, because only with this we can understand how each site really reacts also on long-term changes or long-term influences on different parameters. And only with this we can get an idea of the frequency and the magnitude of movement, which this is an information we need also to produce a good risk map, not only susceptibility map, but go further. And this is why, yeah, it's important. And the surface monitoring, I think I told you most of the things we're doing. The subsurface monitoring as well. So everything I mentioned we have here. Maybe a short note that the automatic ERT is done by the Geological Survey of Lower Austria. So we're also working together with the colleagues from the ministry. And they're also quite interested in this site. Why they're interested, you will see in a minute, because this is also unique for our sites, the anthropogenic embedding. And the second one is the Hofermühle. It's also shallow, but it's more complex. It has rotational and translational features, and it's also coupled torrential system, which sometimes debris flows are happening. And you see also the area is much more bigger than the Salcia area, for example. But interesting here is that here we have a coupling of a slow-moving and fast-moving system. Here. And yeah, Brandstadt, I already told you, it's the biggest area we have. Also, we expect here the depth of between 20 to 40 meters. And but we are not sure yet, but we got a grant recently when this which allows us to have a deep drill. So not with our drilling rig, as you saw, we cannot go too deep, but we will have now a company drilling for us around, yeah, maybe 40-50 meters, we will see. And also Brandstadt is one of the most active ones, so we have around 20, sometimes 25 centimeters per year of Okay, so let's jump into the Salcia landslide. As I told you, it has one speciality. This is the strong anthropogenic influence, and also the surrounding. Here, the surrounding, we have populated areas, so there are houses everywhere. And also below these 3 houses on the right-hand side, there are many more houses. We know that all the landowners there have some problems with material and in their houses sometimes, especially in their cellars. And this area is this site is quite interesting, as it was former times a skiing area, but they had to demolish the skiing infrastructure because the lift was always tilted, and this is why they stopped operating in the 1960s. And also before, we already had some documented activity, some faster reactivations in the 70s and the 2000s. This is also why the Geological Survey is interested in this area. And yeah, it's characterized by this, in this blue zone, we have highly weathered soils and anthropogenic overprint. And from this map here, you can already see that on the left-hand side here, it's quite steep. Then yeah, this round structure is connected to horses, which are yeah, more or less living there since 1 or 2 years. So the landowner introduced some horses there, which also the ground is quite muddy, and this is not so easy for us using the UAVs or the TLS scanner, because they reform and restructure the surface quite a lot. This is yeah, a bit challenging for us. What is also, as I mentioned now, the laser scanner unique here, that we have a permanent laser scanner which is scanning every day at the site. And you can see here already indicated here this lobate structure here. And if we look at the next slide, you can see the lobate structure. We have an increase here in height and surface displacement. You can also see the scars where the material is basically lost in the red area. It's always quite interesting when we go there because the landowners or the one person who owns one house is always asking us how the landslide is doing, is it stable, and if we can buy the property and build a house on it. But yeah, we are always a bit reluctant and say, yeah, well, we will see. Maybe not now. But yeah, you see we have lots of different monitoring systems, but due to time reasons, I will skip that, and you heard already about it. Here, also what you already saw in the Brandstadt case, we, with the DPH and the kilometers, we try to identify the sliding planes, and most likely we have here 2 sliding planes, most likely one at the depth of 3 meters and one at the depth of 9 meters. And yeah, this is very interesting site for us due to the anthropogenic influence, and also due to the houses which are around, which display quite a hazard. Also let's see, there's something in the chat. Okay, I will come to that later. Yeah. Thank you for the question. Yeah, so sum up this Salcia landslide. So we have, as I said, it's our slowest landslide, with only displacement rates of about 15 centimeters per year. And yeah, we created with the methods we used a subsurface model, which allowed us to more or less identify 2 sliding planes. The challenges is the growing periods, of course, and the vegetation cover for our remote sensing applications. And yeah, with this year, we want to further investigate the relationships of the hydrometeorological data, the groundwater, soil moisture and precipitation, and the subsoil and surface movements, which are, as I said, also hard to tackle for us. But yeah, we are working on it. Okay, the second study site I want to show you is the Hofemühle slide, which has its uniqueness concerning this connection of slow and fast moving components. And this is a slide which shows you the landslide itself, the 2 pictures on the right hand side. And if you see here, if you go more left, you see the 2 scan positions where we always scan the slope. And if you go further, you can see also here a map of Austria and where we are located. I think I didn't show that before. And here again, it's indicated the Flush zone, at this highly prone zone to landslides. Yeah, so with the scan positions, you see we can identify, we go down to a slope, and here we also can identify 2 systems, which are most active and most interesting for us. And if we look at subsystem 1.1 and 1.2, if you look a bit more to the west, you see here also this torrent, which is interesting for us. You can also see that there is a scarp, and it's very uneven here, and this is very, very active, and there is a danger that debris flow can happen again, as it did 2013, which partly destroyed here some parts of the house. That's why the Austrian authorities built a protection dam here, and the important street is just below the house. So that's why it's also, from a risk point of view, an interesting study site. Yeah, here you can see also a short history of the landslide. It's also documented very early time. We have main landslide area from 2019, where we have this reactivations with the debris flow I mentioned. And what is particularly interesting in this site are the drainages. So the farmers in the area are quite aware of what is happening, they are quite aware of what's happening. And in the past, and also this is still one adaptation measure which is used today to build drainages. But in now they are at least mapped and we know where they are, but in the past it was not always very clear where these drainages were located. So we are also trying with other geophysical methods to investigate or to see where the drainage pipes are. We can see some endings of the pipes in the torrential system, but we don't know if they're still active, if they're still working, because also broken drainage pipes can be like a trigger for a landslide. When you can imagine when parts of this parts of the drainage or the drainage in the upper part still works and accumulates water, and then you have a breakage of or a leakage, then this can also activation of landslide. There is a question, please.
Just as a layman, I'm Dr. Dhawan from Delhi. How reliable is your data? See, because everything will go out through the data.
Sorry, what level is the data?
How reliable is the data that you are collecting?
Yeah, so as I said, with the laser scanner, we have and the UAV together, we are in the level of very small centimeters. So what you see on the right hand side is very high resolution. The data from the history of the data here we have mostly from reports from the Geological Survey. And yeah, as I said, the other methods, the precipitation, for example, it's every 5 minutes, and the scans we are doing maybe every 3 months, and the UAV flights maybe every 2 months. This is how the data is, the level of data is here. And in this site we started 10 years ago. And yeah, since then we have this surface and subsurface monitoring going on continuously. Of course, we also have some geomorphological mapping, some GNSS measurements, and of course we also have some automatic inclinometers, which also sends directly the data to us remotely. Yeah, also here at Hofemühle, we did this kind of a cross section, which you can see here. And yeah, sliding planes are also in a depth which we expect here of around 10 meters. But yeah, we are working on it, and we have some new ERT data hopefully soon. We already did the site and the field stay, but the results we don't yet. Here, I wanted to show you with this slide the correlation between the hydrometeorological parameters we have and the inclinometer measurements. And we can nicely see here in blue on the x-axis the precipitation, and in the different colors of the lines are different, or these sections are different kilometers with different depths. And you can see here, the movement is mostly connected to precipitation events. Depending also, but also of course depending on depth. So if we look more into the upper part from 0.5 to 2 meters, you can see that it's much more reacting on it than go to a part. Okay, so to sum up the Hofemühle landslide, we have 2 active subsystems with different magnitudes and process rates and also types. As I said, rotational and translational landslides. You have several activations in 2011 and 13. And the monitoring, maybe interesting to note is what I mentioned, that the inclinometer rates are usually low now in January and are highest in February and March when we have snow melts. And the most active areas, we also have the most fluctuations in the groundwater table and in the inclinometer deflection. The outlook is that we want to get deeper into the temporal high resolution relationships, and also with the hydrometeorological parameters. We now did also first measurements of runoff and see when especially when it's raining, to see also what kind of drainage pipes are still working or not. Okay, then I want to come to the last slide, the Brandstadt slide, you know already. So this is our newest slide, as I mentioned. There were already some documented movements, evidences in the early 60s and the 1960s, some reactivations, and also this is why the Geological Survey of Lower Austria and of Austria went there and had some in-depth investigations of ERT, for example, already, I think, 12 years ago or so. And here we have, of course, also highly weathered soils, and the anthropogenic overprint is right-hand side. It's highly used. And we also have a displacement rate, which is quite high. And as you will see a bit later, that we just recently started to implement and to also all the inclinometers here, for example, we already had, I think, half of our inclinometers sheared off already. So the site here is very, very active. And up to now, we could identify 4 different subsystems. Map the right-hand side, you know already. And these subsystems have different process characteristics. So if we look at them, this is the view towards north, more or less. You can see here the sub-area 1 on the right-hand side. This is where inclinometer A was, which I already mentioned to you twice, and we lost it already twice. Reinstalled it now the 3rd time, and we'll see how long this will go. A problem also concerning anthropogenic influence, you can see here this digger, which is located here, because next to the road, there is constantly material transported on the road due to the landslide, and this material is transported here. They're leveling the ground, and then this leads to more ground movement. So we can detect that from our landslide here, from our inclinometer here, and you can also see the different sub systems here with this nice lobate structures you can find here, and also up here and here. So this is how we could identify the different areas. Also, in each area we have, well, not in area 2, but in the other areas we have meters, and we can also see that the movement direction is different. So this is why we come to the conclusion that there are probably different sub areas, but we think we have a very deep slow-moving landslide, and we have some smaller landslides within this bigger landslide. Right here. But you can see here that the infrastructure is constantly damaged, and need to imagine that we have big trucks going there every day to catch the milk from the farmers, have the tractors running there every day, driving there every day, and they are renewing the street several times a year, and this is always quite costly. And this is why also the municipality and the landowners are very interested in our work and support us the best they can. And here you can also see the installed inclinometers and how many we lost. So the one we lost 1, 2, 3, 4, 5 in February and April, which relates again to the snow melt period and the rather wet spring we had in 2023. This is why not all inclinometers now are still active, but we are planning to go there again in 1 month, and then we see 2 months for installing new inclinometers. Okay, I see that it's already 12, so I will be quite quick with the last slides I have. With the inclinometers here, this is also regarding the different patterns of the displacement, the depth of displacement and the direction of displacement, which you can see here quite nicely. Inclinometer A goes more in the northwest direction, whereas C and D go more to a northeastern direction. So this is why we come to the conclusion we have to distance of the depth is always. And currently, colleagues are in the lab for having a look at the sedimentological characteristics, and we hope to get some information quite soon about. And also the most active part is the one I showed you, also where the digger was on inclinometer AA here in the. Okay, so we also here see some correlations to strong or long rainfall, which led to also strong changes in the groundwater level, and this most likely also has effects on the shear strength of the material. But as I said, with the particular characteristics of the soil, we are not there yet. To show you also how a high precipitation event here looks like, and especially how the area looks like afterwards. That you can see here where our inclinometers were, the red dots, and how the systems or the material around it looked like, and how active this area was in April. And on the left bottom side, you can see it was really an extraordinary precipitation event, which was never recorded in the area before. It's also led to a lot of landslides, not only here, but also in other areas. Okay, so we see the total here, like again, a small wrap up of the Brandstadt slide. So the high precipitation event here was double the amount as all precipitation events recorded previously in the year, and we have a significant increase in the sliding activity in all subsystems. We also have the activation of a new subsystem on this landslide, which is quite interesting for us. And we, as I said, 4 kilometers sheared off, and it always at various depths, and the total displacement was up to 20 centimeters just after that event. Okay, and to conclude, or to sum up, but the last slides are on numerical modeling. So my colleague Alejandra Donato, she is doing her PhD also regarding modeling approaches. I just want to show you some results from Avaflow, from a colleague from the University of Graz. And you can see here the Brandstadt slide with different viscosities and how this landslide, if it would be activated in a certain way, how this would influence, if you look on the right-hand side, the rather liquid phase, how this would block the valley and would have very big impacts on socioeconomic values here in the valley. Okay, to the last slide concerning is how we embed our work, our field work, also in the university context in teaching. So we usually have a master program. It's called Geography, Global Change and Sustainability, and one specialization in this is geomorphological systems and risk research. Then we have different courses where we take the students out to the field for 1 week and introducing them to the field methods. They are doing mapping and installation of clinometers, and later then they are working also with the data. We have some excursions here in Lower Austria, and I'm not sure if you are aware of the big Interprevent conference, which takes place this year in Vienna. You are warmly invited for the conference. It takes place we are also one excursion I'm leading to our landslide observatories here in Lower Austria. So if you're interested, just have a look at Interprevent 24, and you can register there since the beginning of January. Okay, so what is our outlook? We want to use the previously built infrastructure and the data we have. Of course, keep on with our field campaigns, but also, as I said, further implement new approaches. And let's say our last, or the thing we would like to be in some years is to implement also early warning system, which works for the area, but maybe also beyond. Okay, so with this summary of surface monitoring, or with the summary starting with the surface monitoring, I would like to conclude. I hope I could show you that we have a spatially heterogeneous sliding activity and process domains in the areas. We're using multi-temporal UAV and TLS datasets to do so, to also detect the even or especially the slow magnitude surface changes. And for us, the most important thing is the vegetation filtering. Then I hope I could show you that also some things about the subsurface monitoring systems we have. It's spatially heterogeneous, and we have non-uniform displacement patterns in depth. This is why it's important that we have the point information also quite spread out around the slope. The inclinometers for us are useful and powerful tool to see low and high magnitude displacements. And as I said, we are now, or we already have some, but especially in Brandstadt, the drill core analysis is now taking place, where we want to identify also especially the soil characteristics in certain depths. The challenge is, we have the characterization of the deep-seated processes is a bit hard for us. This is also this is why we start using now again the ERT surveys, and also with deep drilling we are anticipating this year, want to get some new information about that. And yeah, the outlook, I said already, we want to combine all the different data we have and develop maybe some first early warning system ideas. And with this, thank you for your attention. And if you have some more questions, I will have a look at the chat. I'm very thankful for the questions, and thanks for listening. And yeah, I'm open for questions. Thank you.
Thank you so much, Dr. Philip. So we can see some of the chat questions that we have, then we can ask if there are anything in the participants. Just opening the chat. You can also read there.
Yeah, I'm just reading it. Yes. So, what is the main cause of the landslide failure? So we have, I think it's a mixture of the preposition we have from the geological and lithological background. So it's dynamic in any way, everywhere. And this is like this. The first of the three factors you usually look at it in landslide research. The prepositioning factor is the geology. And the triggering factor when the landslide is activated is, in our case, either precipitation or snowmelt. I hope this answers the question. So there are two more. What was the diameter and wall thickness of the inclinometer? So the diameter is, I think, around 8. So the tube is 8 centimeters, I think, diameter, or 7. And the wall thickness is maybe, it's not much. It's maybe half a centimeter or so. So it's like this normal, normal plastic tubes with some features on every 90 degrees angle where we can pull in our probe, because the probe has some liners, some rolling liners, and then we can put it in. And then we turn it around, so we have a measurement of every from every angle, let's say. I hope this answers the question. There is something longer from Andrew. Yeah, okay. Yeah, thanks, Andrew. We are also looking at this shape array because, as you said, or as we now experienced in the new landslide, that it's so active. We didn't expect that so much. So also we need to think of a different solution, and we thought about this as well. But thanks a lot for this tip. I will keep it in mind and discuss it next week with my colleagues. Thank you. Okay.
Yeah,
okay, I think one other question is for you, Nelima, for where to find the lecture.
Yeah, we are recording the lectures, and it will be uploaded in ISMG TC220 YouTube channel and also Indian Geotechnical Society YouTube channel. You can check that. It will be done in a day or two after, today.
Okay, and then I will see the last.
How does the lithological feature say subsurface profile was found different from the place showing various level or extent of the movement?
Yeah, okay. So I think it depends a bit on the sites, because also the lithological features are at each site a little bit different, and we are in this in this transition zone between this Klippen zone, the calcareous Alps, and our Fluss zone. And about there are some rare information about the lithology really in depth, but not exactly at our sites. So we need to, as I said, we will have a deep drill this year. Hope maybe in 5-6 months or so, and then we will then we can relate better the lithological features to the movement of the ground exactly. So I hope this answers the question. So we are at it, hopefully soon. Between competent and incompetent layers, yeah. So the movement is usually when we have a change from the very clayey part to more yeah, a more limestone-ish part. It also depends a bit on the study side, but there we can see really a difference of the resistance, and as you saw also in the displacement of the inclinometers. But as we also expect in Brandstadt, for example, a shear depth. The depth of the landslide is 30 to 40 meters, but as I said, this we still need to.
Okay, thank you so much. I think we have one more question. Is movement between the competent and incompetent layers?
This is what I was just talking about already.
Okay, got it. So done, I think. Okay, I think Andrew has to leave.
So, and if there are some more
any questions, please unmute yourself and you can have interaction. That will be great.
And I will also write my mail address in the chat, because I also need to leave. That you can just drop me an email with the questions, and then I'm very happy to answer.
Okay, nice. So I think already Philip has shared the email ID. So interested participants, they can just be in touch and other things. So thank you, Philip. And that's a great, understanding. I got it. And though I was in Vienna for quite some time, but next time I'll try to make a visit to your site also. Thank you so much. And I thank
Thanks a lot.
Participants. Yes. EGU, I'm not coming this year because I'm preoccupied. And
okay. Yeah, also if someone is coming to EGU, can have a chat. No problem.
Yeah,
I'm happy.
Maybe Kunal can do that. I think Kunal, are you there? So
Yeah,
thank
ma'am.
you so much. And yeah, you want to take over, right? So Kunal is my PhD students. Okay, so who helped me a lot in organizing this lecture series. And Kunal, can you take over with a vote of thanks?
Yeah, ma'am. So thank you, Philip, for this wonderful lecture and taking out time for. I would like to thank you for taking out time for this lecture. Great. We would like to hear from you in the future series also. Thank you.
Yeah, thanks very much for having me. It was a pleasure for me.
Small information to other participants. Again, I'm just repeating, as a part of international conference which will be held in 2026 at IIT Indore on field monitoring in geomechanics. So we are starting this monthly lectures to connect with everyone from industry, academia, and other things. So there will be another lecture. This month we have 2 lectures because last month we could not have it, so just postponed. So we have another one on 26th. So all the lectures are recorded, and it will be great to interact with the speakers and learn from each other experiences, because landslides is very serious geo disaster that we are facing even in Indian terrain. So thanks everyone and for joining. Thank you so much. So we are closing the session. Thank you. Thank you, Philip.
Thank you. Bye bye.